Hi folks, so this will be the last video for National 5 Physics, and in this one we're going to be looking at what we're going to call cosmology. Now in the earlier sets of videos we were looking at other parts of the space physics course such as space travel, but this one we're really cosmology. If you look up what the definition of cosmology is, cosmology is the study of the origin and then the development of the universe, and you've got to realize that this is what I'm going to say. This is our current understanding. This theory that we have of how the universe began has evolved over time, and probably the best I can say is that we would call this, at the moment, this is our best guess to what has happened. We're looking at evidence that we can see, but we don't really know because, well, I guess nobody was around to see. We can only infer what has happened by what the science is telling us. And so we're going to give you a very brief introduction to cosmology. We'll look at a couple of different aspects of this. We'll look at some evidence and discuss a bit of the evidence that we have for why we think that the universe has began and developed in the way that we're going to say it is. So, as ever, let's look at the learning intentions, see what we need to know first. And here we are with cosmology. So I can correctly use the term light year. You should have come across this before, but we'll explore this a little bit more. I can convert between light years and meters. We're going to do some practice calculations of this. Then here at 8.3 I can give basic description of the Big Bang Theory of the origin of the universe. I know that the estimated age of the universe is approximately 14 billion years or 13.8 billion years old. Then I can describe how different parts of the electromagnetic spectrum are used to obtain information about astronomical objects. And finally, I can identify continuous and line spectra, and I can use spectral data for known elements to identify the elements present in stars. So we really have four things there. So we're going to talk about light years, we're going to talk about the Big Bang, we'll look at electromagnetic spectrum and how we use information from the electromagnetic spectrum to look at space, and then this thing called spectra finally, and that'll be us. So we'll start off by looking at light years. Light year is simply defined as the distance that light will travel in a year. Now we know, or you should know already, that light travels with a velocity of 3 times 10 to the power of 8 meters per second, or 300 million meters per second, which is a phenomenally fast speed. Indeed, it's the fastest thing that anything can travel in the universe. That is the absolute limit. Nothing can travel faster. In fact, nothing other than electromagnetic radiation can actually travel at the speed of light. It is only electromagnetic radiation that will do that. So let's go and have a look at some of the calculations that you'll need to do. And so light years, well, let's just get a definition first of all. And there we have it, the distance that light will travel in a year. Now it seems a bit counterintuitive to say light years. Well, we're talking about time then, surely, with a year. It's just the way it's called, and that's it. So what is a light year, if we actually put a number on it? Well, we can do a calculation, and so let's we'll start with a table, and it's going to be speed, distance and time. Now we know that light travels at 3 times 10 to the power of 8 meters per second, and we know that, given the definition, the time that we have is 1 year. And the distance, well, that's what we're going to try and calculate. So we'll have distance, our formula will be distance is equal to speed times time, or d equals vt. And you could potentially make your conversion in here, but I'm just going to show you the calculation as how you would write it out. So speed, we'll have 3 times 10 to the power of 8 times the time, and so that is 1 year, and in in 1 year there is 365 days, because if this is meters per second and we want to answer in meters, then we've got to have a year in seconds. So 365 days, there are 24 hours in 1 day, there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. Type this into the calculator and we get 9.4608 times 10 to the 15. Let's call that 9.46 times 10 to the 15 meters. So light will travel 9.46 times 10 to the 15 meters in 1 year. Let's put this into some context now. Okay, so where could we start? Well, I guess, well, if we look at, first of all, how long will light take to travel around the Earth? So if you had a little bit of light and in some way that you could make it travel in a circle around the Earth, how long, in theory, travelling at 3 times 10 to the power of 8 would it take to go around? So how long does it take light to travel around the Earth? Well, the Earth has a circumference, and so we can say distance. The Earth has a circumference of 40 million meters, so 4 times 10 to the 7 meters, so 40 million meters, and we know it's travelling at 3 times 10 to the power of 8. I'm going to look for time, so how long does it take for light to travel around the Earth? So time would equal distance over speed, and we'll have 4. I'm having a problem drawing my 4s today. There, over 3 times 10 to the power of 8. We're going to get 0.13 seconds. And so so what that's basically saying is that light would be able to travel 7.5 times around the Earth. So make 7.5 complete revolutions of the Earth in 1 second, which is phenomenally quick. Okay, so let's have another one. The sun, how long does it take for light to travel from here to the sun? Or how long does, I guess, because we get our light from the sun, how long does the light take to reach the sun, to Earth? And so we know that light is always going to travel at 3 times 10 to the power of 8 meters per second. The distance from here to the sun, 1.5 times 10 to the 8 meters. Wait a minute. Well, that's clearly not right. I'm getting my numbers in kilometers rather than meters. So in meters, it's 1.5 times 10 to the 11. And so let's have a time. We're going to look for the time, calculate time. Same formula as before. Time is distance over velocity. 1.5 times 10 to the 11 over 3 times 10 to the power of 8, which gives us 500 seconds. Now, if we divide that, well, let's divide it by 60. No, hang on. We get 8.3. 8.3 minutes. And so what we could say is that if it takes the light 8.3 minutes to travel from the sun to the earth, we can say that the sun is 8.3 light minutes away. So the sun, we're now, we've turned a time here into a distance, and we're going to say that the sun is 8.3 light minutes away. And we can do that rather than saying the sun is 1.5 times 10 to the 11 meters away. We say 8.3 light minutes, and that's a distance. So we've given a distance here as this light minutes. And the reconversion, if you're saying if we've got 8.3 light minutes away, then we can do the conversion into the distance in meters just by taking that and rearranging that. So 8.3 minutes would be 500 seconds, and we would have distance is 3 times 10 to the power of 8 times the time, which would be 500 seconds, and we would then get out 1.5 times 10 to the 11 meters. Okay, so we'll do another one, and this is now the closest star. So the closest star to us is Proxima Centauri, and that is, we have a number here, 4.2 light years away. So there we go. Calculate the distance in meters of Proxima Centauri, which is 4.2 light years away. Okay, well, we'll just, as before, speed, distance, time. And we've got distance, we're going to be looking for distance. We have our velocity, which is, oh my goodness me, Mr. Garrett, come on. 3 times 10 to the power of 8 meters per second, and a time. Now, it takes light 4.2 years to travel from that star to us on Earth, and so we would have a time of 4.2 years. Make our substitution, so we're looking for distance is equal to speed times time. Three times 10 to the power of 8 times. Now, before, when we did our initial calculation to find out the distance in meters, we ignored the 1 because the time was 1 year, and we didn't actually write the 1 in there because, well, it does nothing, putting a 1 in a multiplication calculation. But in this case, we have 4.2, and 4.2 will affect our results, so we're going to put 4.2. And then, as before, 365 days a year, 24 hours in an hour, 60 times 60. And so 365 times 24 times 60 times 60. And that will give us, give me a second. So we have 3 times 10 to the power of 8 times 4.2 times 365 times 24 times 60 times 60, and we get 3.97 times 10 to the 16. So 4 times 10 to the 16 meters, which is insanely far away. Some estimates would put that if we were to try and go there in a spacecraft with current technology, it could take us about 75,000 years. It's not much use. So right now we aren't going to go and visit Proxima Centauri anytime soon, unfortunately. I hear it's kind of nice there at this time of year, but oh well. Okay, what else do we have? Well, I guess Milky Way. If you don't know, Milky Way is our galaxy. We are we're in the Milky Way. And if we were to try to travel from one edge of the Milky Way right across through the middle to the other side, so if we were to try and span the diameter of the Milky Way is 100,000 light years across. So if it takes us 75,000 years to go 4.2 light years, we are not getting across the Milky Way anytime soon, not until we perfect the first warp engine. So there we've done a number of calculations converting light years, the number of light years into a distance in meters, and we'll do one further calculation. Although we've done here we've taken a distance in meters and converted it into, well, I guess into light minutes. We've not had one where we're taking a distance and converting that into light years, and so we'll do one further example and then we'll leave light years alone. And so that would be, I guess, Sirius. Sirius, known as the dog star, the brightest star in the sky. And so Sirius is 8.136 times 10 to the 16 meters away from Earth. Calculate this distance in light years. And so the process is kind of the same as before. What we're going to be doing is we're going to be looking to get time. And so we'll have speed, distance and time. Oh no, I'm using a black pen when I should be using a blue pen. What I do is stop the video and restart and record. I'm just going to scribble over it and it's going to make a mess and I'm going to be very upset. But okay. So 3 times 10 to the power of 8 meters per second. Its distance is 8.136 times 10 to the 16 meters. And we're going to look for time. So time is distance over velocity. And we're going to have 8.136 times 10 to the 16. 3 times 10 to the power of 8 meters. Okay, so we'll get a fraction, 8.136 times 10 to the 16. And this gives us, what would this be? 1, 2, 3, 1, 2, 3. So 271,200,000 seconds. Yeah, I'm not writing that. So 271.2 times 10 to the 6 seconds. Now, this is the tricky part. Before we've sort of stopped here and that's been fine. But what we're being asked to do is to calculate in light years. This is 271.2 million light seconds, but that's not what we're looking for. We're looking for light years. So we now have to do this further conversion into light years. And what we'll do to convert this from seconds into years, we divide this number by the total number of seconds in a year. And so for light years, we'll have 271.2 times 10 to the power of 6 divided by the number of seconds in a year. Now it's the same as before, so 365 times 24 times 60 times 60. Wait a minute, was that? Yeah, okay. And then here we go, so 365 times 24 times 60 times 60. And it gives us, which equals, let's call it 8.6 8.6 light years. So Sirius is 8.6 light years away from Earth. That's all we're going to do in light years. If you can convert the distance in meters into light years, and if you can convert the distance in light years into meters, we're done. Good. So we have the distances in space thing covered. It's not the only one that we use, although it's the only one that we really need to know about. We have within the solar system, we sometimes use a unit called astronomical units. One astronomical unit is the distance between the Sun and the Earth. And then we scale everything according to that. You might also see listed as something called parsecs, and I'm not even going to begin to get into parsecs just now. It's complicated, but that's another unit that you may see as coded distances in space. Parsecs would be used in a similar way as light years for a galactic and universal scale. So, on to the Big Bang. So the origin of the universe itself. Now, we estimate that the universe is 13.8, possibly 14 billion years old. And what happened? Where did it start? And then how do we know? So this is what we're going to be looking at now. Okay, so the universe started, we think, as a singularity. Now, what is a singularity? Well, a singularity, we think, is an infinitely small, infinitely dense, and infinitely hot point in space. I guess that's the basic definition of it. So it started as a singularity, and then the Big Bang happened. Now, it would be a mistake to say that there suddenly was a great explosion, because this is not what we talk about. We don't want to give you the idea with the Big Bang that there was an explosion and suddenly everything happened. But and what we would say, the Big Bang happened and then there was a rapid expansion. And we've got to get this idea of being an expansion rather than an explosion. So this expansion started happening. Now, as the universe started expanding, there was a lot of energy. As it started expanding, it started cooling down. And what we think happened is that the energy that was created in the Big Bang, or the energy that was there at the Big Bang, was converted into matter. And this is explained. Einstein's famous equation, E equals mc squared. The very basic principles of that equation say, and indeed what Einstein said, was that energy and matter are manifestations of the same thing. In saying that you can convert matter into pure energy, and vice versa, you can convert energy into matter. And so what we think happened is that this energy was created into matter, both matter and then antimatter, and we think that there was equal amounts of matter and antimatter created, and generally what happens is that the matter, when matter comes into contact with antimatter, they'll come together and annihilate each other, and as they're annihilating each other, then they'll release a lot of energy, and that's the reconversion of matter and antimatter into energy, that reconversion of the energy. For some reason, although there was equal amounts of matter and antimatter created in this universe, we have a matter universe rather than an antimatter universe. And so in our matter universe, something happened, and we don't really know why or what caused this, but when the matter and antimatter started annihilating each other, there was matter left over, and nobody really knows why. So we've got to this point, and I guess if you're looking at a time scale for this is occurring in fractions of seconds, a fraction of a second. And so the universe at this point is still less than a second old. At about a second, just to give a number on it, the universe had cooled sufficiently to allow the formation of protons and neutrons. So the formation of these fundamental particles. In higher physics, you'll learn about even more fundamental particles than protons and neutrons. I know you've been told up until this point that a proton, a neutron, and an electron are the kind of three building blocks and the fundamental particles. But what we now know is that protons and neutrons are actually composite particles. They're made up of something else. So around about a second, the universe had cooled enough so that these protons and neutrons could start to form. The cooling continued, and around about after, I'm guessing, 3 minutes, the temperature, now we're talking temperature, is below, I think, 1 billion degrees Celsius. So the temperature is cooled to 1 billion degrees Celsius. And this is allowing the protons and the neutrons to finally start to come together. And when you have this, then you're starting to get the nuclei of atoms forming. Now it's the nuclei of atoms, not atoms themselves. So we're getting hydrogen nuclei and we're getting helium nuclei, the first, I guess, recognizable forms of matter that we have just now. About another 300,000 years of cooling. So our universe temperature is now around about 3,000 degrees Celsius. And finally it's cool enough and we've lost enough energy that the electrons that were there can now start binding into these nuclei. And so the universe is 300,000 years old and we're now starting to get the formation of the first atoms. And so we'll have hydrogen gas, we'll have helium gas. And this is really what we have at the start of the universe. This creates these huge clouds of gas, these huge stellar nurseries, nebula, these huge clouds of hydrogen and helium gas. And what happens with that is that you'll have a random meeting of two nuclei that just sort of come a little bit too close and that they start to become gravitationally bound with each other. And this forms a bigger sort of clump of gas, a more concentrated area of gas, and which has a larger gravity than the surroundings. And so then the subsequent hydrogen atoms and helium atoms can then start being drawn into it. And you get this sort of chain reaction, this ever increasing mass in the middle of this cloud of gas. And once there's a sufficient concentration of this, and now if we're talking about on the universal time scale, we're looking at about 100 million years, then we're having these concentrations of gas that are concentrated enough. And what happens is the gas comes together, the gravity from the gas starts to squeeze all of the other atoms that are in this ball now. And as it squeezes it, it creates a pressure, and the pressure creates a temperature. And when the temperature and pressure are high enough, and so we're talking 100 million years after the Big Bang, then we're starting to get the first formation of stars. And what a star is a star is a big ball of gas that is undergoing nuclear fusion. Nuclear fusion is the process where light elements will bind together to form heavier elements. And so in this case, we're talking that the hydrogen atoms are binding together to make helium. And in the process of this, again, E equals m squared, E equals mc squared. When you join two hydrogen atoms together, you're losing a tiny amount of mass, and this loss in mass is converted into energy, which is the energy released in a nuclear reaction. And you can, if you know the mass lost, you can multiply that by c, which is the speed of light, so c squared, to get the amount of energy released. And so for these formation of stars, as the temperature and pressure increased inside, it became hot enough and pressurized enough for hydrogen fusion to start taking place, and stars were then born. From that, we would get clumps of stars, and these clumps of stars would then form the galaxies, and there are billions of galaxies in the universe that we know of. So that's really the kind of timeline of the Big Bang. If I was to sum that up in a nutshell, at the start there was a singularity, then the Big Bang happened. From that there was a rapid expansion and a cooling of the universe. As it cooled enough, it allowed the formation of the first particles, and that then led on to the formation of clouds of gas, which then led on to the formation of stars, which then led on to the formation of galaxies. And here we are today, 14 billion years or 13.8 billion years later, we have what we see around us. And so that is the Big Bang theory. And so the next step, I guess, is how do we know this? You know, this is, you could just say, well, that's a good story, Mr. Garrett, but, well, how do you actually know it? You just sort of said a lot. We weren't around, and so how do we actually know it? Well, there's a couple of pieces of evidence, and again, this is one of the things that we get into a lot higher, and we actually look at the evidence for the Big Bang in a lot more detail. I'm going to just try and keep it really, really simple here without getting too deep into sort of pretty heavy physics. But, well, the first thing would be if we're looking at the expansion of the universe. So, i.e., the universe is getting bigger. And it's something which we call Hubble's law, and astronomer Edwin Hubble first discovered this. And I'll go, give me a second, I'll go back to my notepad. So we've got this guy, Edwin Hubble. And he, through various means, which again I'm not going to get into, he started looking at stars and he found out two things. So he found out how fast they were moving away from us. Incidentally, we look at the stars and all the stars are moving and almost uniformly stars are moving away from us. And so we don't really see stars that are coming towards us, which is kind of strange, but that's not what we expected. It's certainly not what Edwin Hubble expected when he started doing his work and looking at this. He thought that he would see some stars that were moving towards us, some stars that were moving away from us. But what he found is that just about everything in the universe is moving away from everything else. But what he did was he came up with a graph. And this is a very famous graph. And he looked at the speed that the stars were moving away from us and the distance that they were away from us. So imagine that this is us here. And he found a star that was this far away from us, and it's moving away from us at a certain speed. And so he plotted that on his graph. Okay. And then he found another star down here. This one's slightly closer by. It's moving away from us. And he found that if the star was closer to us, then it wasn't moving as quick. And so in here. However, if the star that he had was really far away, moving away from us, he found that it was moving away quicker. And so very quickly he got this relationship that the further a star away from us, the quicker it's moving. And we had this lovely directly proportional graph, and I'll show you one. And so there you go. This is actual data of 1,355 galaxies, and you can see that there is a definite correlation between the velocity here and the distance of these galaxies. We're getting a clear straight line relationship here. So what does this mean? Well, what it basically means is that if this galaxy has traveled this distance, so let's just do some physics here. So time is distance over speed, and so the distance here is small, but the speed is small. So distance here and speed is small will give us a time. Here, again, same formula. The distance is medium, but the velocity here is medium. And what we find is that the time that we get is exactly the same. And here, star up here, the distance is big, the velocity is big. We do distance divided by velocity, and we will get exactly the same time. And every single star, roughly speaking, every single star, we get the same time. And that time is 13.8 billion years. And so if you took that and rewinded it, then 13.8 billion years ago, then suddenly when the stars are all doing this, you rewind, the stars are moving together, and the stars that are further apart are moving in quicker, the stars that are close by are moving in slower, and eventually you get to a point where they all come together 13.8 billion years ago. And so 13.8 billion years ago, from evidence that we can see of how quickly the stars are moving away from us, suggests that they were all in one place 13.8 billion years ago. So that is the first piece of evidence for the Big Bang. We also have something, and when the next part of this video we're looking at detecting signals from space. One of the things that we can look for is we can detect electromagnetic radiation, and light is just a type of electromagnetic radiation. And when we look up into the sky, and if we look up into the sky with a special telescope that detects microwave radiation, then we find that there's this, there's almost a uniform background of electromagnetic radiation, of microwave radiation. And what we're looking at is, again, it's a tricky concept to get your head around, that the temperature of something is directly related to the type of radiation that it gives out. Really, really hot stars will give out a blue light. And now if you think about blue in the electromagnetic spectrum, blue is quite a high frequency short wavelength. Then as stars start to cool down, we find that they become more reddy. The wavelength gets longer, the frequency gets smaller. Okay, so temperature is related to the amount of, to the type of electromagnetic radiation that's given out. And what we find is that if we look in point telescopes anywhere in the sky, then we'll find that there's this background electromagnetic radiation that currently is in the microwave range, and this gives us a temperature. And what we can see is that if we look at the cooling rate of space, the rate at which space is cooling down, and then we go back. So currently the temperature of space is giving out a wavelength in the microwave region, and this is actually called, so it's called cosmic microwave background. Radiation. It's quite often referred to just as CMB. So cosmic microwave background radiation. And what this tells us, if we can predict the rate at which the universe is cooling down, okay, and we know how quickly it cools down, we kind of know how hot it was when it first started, and we can look at this cooling rate and we would predict, well, if we've been around for 13.8 billion years, it started here, it would have cooled to here, and this closely ties in with this microwave, with the temperature of microwave radiation, I guess. And so we have this cosmic microwave background radiation, which again points to a universe being 13.8 billion years old. And in our course notes, what we can see is, if we go down to the cosmology section, Well, first of all, we have the light years, but here we go, the Big Bang Theory, and this is really just what I've been saying in a slightly more concise way. But evidence for the Big Bang, so we've got Hubble's law, we have cosmic microwave background radiation, and if you're asked for evidence of the Big Bang, or how do we know, well, we've got a couple of things there, which is absolutely fine. Detecting signals from space. Okay, so this is our next thing here. Okay, so basically when we're talking about detecting signals from space, what we're really talking about is using telescopes. Now you'll be familiar with what a telescope is. Essentially, it will you can turn a telescope and look at a star, and it will magnify that star. What it actually does is it collects the light and magnifies it or intensifies it. And we use telescopes to look at visible light, and I guess the most obvious thing that you might think of is the ground-based telescopes, where we use the telescopes and we'll place the telescope on top of a very, very high mountain. And the reason for this is to try and cut out as much of the atmosphere as possible. The atmosphere is a problem because as the light travels through the atmosphere, it will become slightly distorted, which is why you see stars twinkle. Stars don't actually twinkle, as I was saying, and so the higher up that we can get, the more atmosphere that we can cut out, then the clearer an image that we'll get, because the twinkling will degrade the final image that we're looking for. Something that we've done in the last few years is to launch space-based telescopes. And this has the clear advantage of that if you just take it out of the atmosphere altogether, then there will be no twinkling of the stars, and we'll be able to get much, much clearer images. There's a couple of problems with this. First of all, the cost involved in launching a telescope up into space, and secondly, some of the ground-based telescopes that we have are truly massive. I mean, they are really, really big things, and big and heavy things, and it would be too difficult to launch something like that up into space. And so we're kind of limited with the size of the telescope that we can have in a space-based telescope. But that's the trade-off with the clarity of the image due to the lack of atmosphere. And so detecting or using the telescopes to pick up the visible light and to look normally, well, we can get really good images of stars, and we can find out what stars are made of. I'll come to that a wee bit when we're talking about spectra. We can look at, we can certainly look at the planets within the solar system. We can get incredible images of the planets, and we can look at our sun, galaxies, and that kind of thing. But it's not the only thing that we can use telescopes for. And indeed, if you look at the electromagnetic spectrum here, visible light is only a very, very small part of the spectrum, and we can actually get information from each one of these different types of electromagnetic radiation. For example, the sun is emitting huge quantities of high energy radiation, such as gamma rays and X-rays, and so we can have a telescope which is designed to detect these high energy particles. Well, we've got the electromagnetic radiation, but we can also pick up charged particles that are being released, such as neutrinos. And so if we configure a telescope to look at certain parts of the electromagnetic spectrum, we can see different things going on. Ultraviolet stars, for example, we can see that you will have things like quasars, which will release an awful lot more ultraviolet light than other types of stars, and so it's one way of detecting different types of stars. Infrared, we can detect heat, so infrared radiation is emitted by all hot objects, so we can tell a lot about the temperature of certain things in space, such as nebula. So stellar nurseries and nebula, we can detect, and we can see kind of what stage of stellar formation is going on at any particular given time. And with radio waves, well, we get a lot of information about the Big Bang. As I've already talked about cosmic microwave background radiation, and so certainly if we're going to talk about radio telescopes, then we would be classing microwave radiation in that radio wave part. But just be aware that looking at different parts of the electromagnetic spectrum, and essentially is we would call it a telescope, but we just don't use light, and so we wouldn't use lenses or anything. For example, I'll show you a picture of a radio telescope. Here we can see that we're looking at satellite dishes essentially, but this is what a radio telescope would be, so they would be able to collect the radio waves. Quite often you'll have these radio telescopes that are arranged in what we would call an array, so a radio telescope array. And this is where we have a number of smaller dishes, but they're all linked into to form one larger one. You can add up the area of each of the telescopes to have a really, really large area. And essentially the point here is that the larger the diameter of the telescope or the dish that you have, the more information that you can gather. Because if you imagine, as we looked at again earlier on, that signals from space is very, very large, and so even our next closest neighbor, Mars, is incredibly far away. Even looking with the naked eye, you can see Mars as just a tiny sort of orange star, and so everything, even our closest, well, I guess I should say our closest neighbor would be the Moon, but apart from the Moon, Mars, and then everything going on beyond that is far away. So the larger the area of the sort of information gathering that we can have, the stronger the signal that we'll be able to get. And certainly if we're looking at trying to look at stars or look at objects from out with our own solar system, then the larger diameter of dish that we can have, the better. And so that's really detecting signals from space. There's a little bit of information here in the notes. I would have a wee read through that. But as I said, the main thing is to be aware that if we're looking at signals from space, don't just assume that we're talking about visible light, that we use all of the electromagnetic spectrum to build up a picture of what's going on out there. And so the final thing we're going to talk about today is spectra. Now, one of the learning outcomes, if you remember, the first thing that it was talked about when we were talking about spectra is I can identify, I guess, the difference between a continuous spectra and a line spectra. And so a continuous spectra, very simply, is a rainbow. If you take, well, obviously the sun, if you look at the sun will give out white light, although it looks yellow, but it'll give out light of every single wavelength. And if we take a beam of sunlight, for example, and pass it through a prism, a glass prism, then it will split up into its component parts, and that being the red and orange and yellow and so on. And so all the different parts of the rainbow, and that would be what would be described as a continuous spectra. So shown on the screen here, we have a continuous spectra. We'll have a red wavelengths at one end and our blue into violet, indigo and violet at the other end, and it would move through a sort of continuous and seamless variance of the colours. Now, so what is a line spectrum? Well, a line spectrum is, the actual explanation for it is quite a complicated thing. And looking at our notes here, where are we going? So a line spectrum, we'll have two different types of line spectrums, and both are equally important. We'll have something called a line absorption spectrum, and then we'll have a line emission spectrum. Now, these are produced in two different ways, but they're relevant to us by different, what am I trying to say? They're relevant to us for different reasons. Now, the line emission spectrum. We can produce line emission spectrum of elements in a lab. And what that means is that each individual metal or each individual element will have an associated spectrum with it. When you heat it up or when you excite it, it will give out colour. There's a video which I'll show you in a short while, which will explain this. So when you heat up an element, it will give it a certain colour. And shown in this box here, you can see that the element, whatever this is, let's say it's hydrogen, it will give it a really, really strong red band in here, but it's a very specific wavelength. And so we can actually identify the exact wavelength that hydrogen will give out, and it will be the same for every single element of hydrogen. If we manipulate the hydrogen in such a way, it will always give out this wavelength. And there'll be these other wavelengths here. It'll be almost like a fingerprint of the element. Okay, and what happens is that if we then look at the light from a star, if the element will give out light, it's also possible for the element to absorb light. And so we can look at the light given out from stars, and this is the kind of thing we would see a line absorption spectrum. And so if we're looking at a star, this is actually what it would look like. Rather than this is a continuous spectrum, is what we would imagine we would get from the sun. We find that it's not actually correct. This is an actual picture of our sun. So we take a telescope or a camera, we point it at the sun, and then we take the light and we pass it through a spectroscope, and then we get an image like this. And you can see it's a rainbow, but you can see lots of dark bands here. So these are line absorption spectra. And what's happening is that the light is traveling from the core of the sun. It travels out through the atmosphere of the sun, the outer layers of the sun, and in the outer layers of the sun there's elements present. Now, if an element will produce these black lines here, well, this is sodium. When you heat sodium, it produces that line, these lines. As the light is traveling out, it will also absorb these lines. And so what we can see is that in this case, if we know in a lab that we have an element that emits this light here, then we can look for that as a characteristic fingerprint in the stars. And so therefore we can identify the type of star. Now what I'm going to do is I'll play a video from Brian Cox, who he makes some of these emission spectra, and then we look at some absorption spectra. But it's a nice wee clip. So watch that.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light, and each element gives off its own unique set of colours. So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac. And copper is blue. Each element has its own characteristic colour. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the colour of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from our sun. And at first glance, it looks very familiar. It looks like a stretched out rainbow, because that's exactly what a rainbow is. It's the spectrum of the light from the sun in the sky. But if you look a bit more closely, then you see that this spectrum is covered in black lines. These are called absorption lines. Each element within our sun not only emits light of a certain colour, it also absorbs light of the same colour. By looking for these black lines in the sun's light, we can simply read off a list of its constituent elements, like a barcode. For example, these two black lines in the yellow bit of the spectrum, sodium, you can see iron. Right down here, you can see hydrogen. So by looking at these lines in precise detail, you can work out exactly what elements are present in the sun. And it turns out that that's about 70% hydrogen, 28% helium, and 2% the rest. And you can do this not only for the sun, but for any of the stars you can see in the sky, and you can measure exactly what they're made of. So that star there is Polaris, the pole star, and you can see that because all the other stars in the night sky appear to rotate around it. Now it's 430 light years away. But we know just by looking at the light that it has about the same heavy element abundance as our sun. But it's got markedly less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our sun. Whereas other stars are metal heavy. Sirius, the dog star, contains 3 times as much iron as the sun. And Proxima Centauri is rich in magnesium. But although the quantities of the elements may vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth.
So you can see from the video that if we take a picture of the sun, or if we take an image of a star, then we can put it into a spectroscope and get an image of the what we will call the line absorption spectra. And then we can compare that to data that we can produce in a lab with line emission spectra. And the typical type of question that you're going to be asked, I can show you here, in that you'll be given something with as an unknown sample. So this, for example, would be a black and white image, of course, but an image of a star, and we have certain elements which we can try and identify within that. Now, this is exactly what you would be asked, and so you look through and you try and find out where the lines match up. Now, we can obviously see that this is not present in the sample, so it does not contain any of element A. And then if we get, let's get a ruler, and then what we can try and do is we can try and match up. So that doesn't quite, well, no, sorry, element we know it's not element A, but element B, well, we have a match there with element B, and we've got a line here, if we can see. So looks like we have a match with element B. So element B is present in that star. Then element C, so we've got this characteristic double band here, and that matches up pretty perfectly there. We've got a match there, so, oh, sorry, yep, that matches, and again on this side we'll have a match there as well. So it does contain element C. And finally with element D, well, we can quite clearly see that these two lines here are not present in there, so it will not contain element D. So from this sample, we can see that it contained within that sample is made up of element B and element C. And there's more examples in the course notes for you to do. Again, I can go through here. So what we're doing, we're just drawing lines, and we're trying to find matches of the elements that are present. So that is us. That's Spectra finished, and indeed that is now Space Physics finished, and that is National 5 Physics finished. So everything is done. We'll be back in school soon enough, and then we can sort of unpick everything that we need to unpick and ask any questions that we need to ask. But for a final time, thanks for watching, and I appreciate the hard work that you've shown and put in over the last many months. Okay, bye.